And without further ado, what Bayesian estimation of elastic constants?
That's right. Oh, is my audio live? I think I hear myself. Yeah, okay. So my name is Ben. I'm from UC Santa Barbara. I'm going to talk to you today about a mechanics problem that I worked on in STAN in collaboration with some material scientists from my university. So the talk itself, I'm going to keep at I'm going to keep it at like a really high level, like exactly what mechanics problem it is we're trying to solve, and from the experience, what lessons did we learn, and in general, what do I think Bayesian inference and especially STAN can do for the field of mechanical engineering. The notebook is a little bit different. So the statistics aren't very sophisticated here. This is more of a computational problem. If there's anything difficult about this problem, it's because we have to solve a weird little PDE or partial differential equation. And the notebook attached to this presentation is about if you have some sort of computational science, some computational science problem, be it some weird sort of partial differential equation or a really exotic ordinary differential equation that you just can't use the STAN solvers, how can you go about sort of writing that, taking C++ code that solves your problem, or C++ code from which you can get your sensitivities or your the derivatives of your output with respect to your parameters. How can you hook that back up into STAN so you can use sort of the C++ stuff you already developed to solve your problem, but then just kind of tack on the STAN statistics stuff. And this builds on stuff that's in our STAN and command STAN already. But the actual presentation is about Bayesian estimation of elastic constants. And the actual materials we're interested in are superalloys. And superalloys are basically the materials used to build jet engines. And so here's a picture of a jet engine. They're somewhat useful. You can also, another application for superalloys is this is kind of I guess more generally they're gas turbines. And this is kind of like the jet engine application. These are kind of small gas turbines. Big gas turbines are just used if you have too many liquid dinosaurs and you needed to burn them off for electricity or something. But kind of the game that people play with gas turbines is they want to operate them at higher temperatures. If you operate your turbine at a higher temperature, it's marginally more efficient. And even if these things get slightly more efficient, they burn a lot of fuel. And so if you can get them more efficient, you make a lot of money. And maybe that's sort of a sad goal to just be trying to make more money, but that's the honest truth of this. The downside to trying to operate a gas turbine at a higher temperature is that metals melt. Superalloys are metals. And if you operate it at too high of a temperature, your components will fail, and sometimes they will fail catastrophically. So just as an example, a real-life example of a superalloy falling apart, this is American Airlines flight B763. This is just from a couple years ago, and this piece of the rotor, it's like a rotor disc, it's part of the inside of the jet engine where all the fire and stuff is, cracked and blew apart, and this airplane did not fare very well for it. I don't think anyone actually died in this instance. I think maybe a couple of people got injured sliding down the ramp or something. But the plane did not fare very well. And pieces of this rotor were found something like half a mile away from or not half a mile. Excuse me, I was half a kilometer. Wrong units. A good thing I don't work for NASA. Anyhow, so So pieces of this rotor were found half a kilometer away from the explosion. And when these things explode, when the actual power generator gas turbines explode, I think it's you find pieces of the turbine in the next county. And so anyhow, the whole goal of this is to understand the materials that go into this, and the small part of gas turbine development that I'm involved with is estimate the elastic constants. And the elastic constants are sort of the basic parameters of material strength. So the simplest sort of mechanics model you'll learn about, and if you've ever taken any sort of undergraduate physics class or even a high school class, you'll have heard of Hooke's law. And that's that's like the simplest mechanics model possible. And it is, if you have a spring and you displace that spring away from its resting length, it will try to like pull itself back together. And the magnitude of the force that it produces is linearly proportional to that displacement. The coefficient of proportionality is its elastic constant. And basically, we try to estimate these elastic constants for materials more complicated than springs. They're still linear materials, they're just more complicated. And I'll explain more about that in a second. So I wonder what the next slide is. Oh, yeah, so how are we actually going to get those elastic constants? Well, believe it or not, this is a STAN conference. We're going to use STAN and we're going to do some Bayesian inference. So there's a model coming. We don't do it quite how you'd expect. So if you might try to like think of what the simplest experiment to get the elastic constants of a spring would be, it's something like maybe tie the spring to the ceiling, put a known load on it, and then measure like how much it's displaced, and you can like do a little division and estimate your elastic constant. What we do instead is a little bit different. We actually try to measure what are known as like the resonance modes of a material, and just when you're thinking about resonance modes, just think of gongs. So if you have like a big gong or a drum or something, and you hit it with a hammer, it rings, and it will ring at a frequency that is a function of its geometry and a function of the elastic constants of the materials that went into it. And much in the same way that we can like ring a gong, we can take a little lump of material, one of these superalloy materials, put it in some sort of ringing apparatus, and figure out where it likes to vibrate, like the frequencies, like the noise that it makes. And the key thing here is that the resonance modes are going to, where the sample resonates is going to be a function of its geometry, and it's going to be a function of these elastic constants. We know the geometry, we want to figure out the elastic constants, and that's a typical experimental setup for this. That cube right there, this is not like big. There aren't like little people here. This is like maybe this high on a desk. So this kind of reminds me of a Zoolander thing. But anyhow, this is like the typical output of an experiment, and we really don't care about the amplitude of these resonances. We just care about where they're at. And if the samples are nice and we don't have any missing modes, we're ready to solve our inverse problem. And oh yes, so just a real quick plug. I have this slide here, but I'm not going to go through it in detail. This is an example that's in the Markdown notebook attached to this. That's just how do you go from something like Hooke's law, which is the simplest sort of linear elastic mechanics model, and compute resonance modes. It turns out you stop by in ordinary differential equation land and then end up in eigenvalue land. That's all you really need to know. Our mechanics boil down to eigenvalue problems, and so it's going to be eigenvalue problems that we need to solve inside STAN, which are kind of the hard things. So I told you about springs. Springs are kind of the simplest mechanics models. The actual materials we work with are more complicated than that. They are single crystal materials, and what that means for like a turbine blade to be like a single crystal is that like it's weird, like it's hard to say and like say with enough like admiration of what it means. But if you have a turbine blade and it's a single crystal, that means, and the turbine blade might be this big. Every atom in that turbine blade is kind of aligned on a lattice, and kind of the important implication here is that because of this, we get like a lot of different sort of elastic constants, and it comes about because, okay, pretend these are our atoms, and like the red dots are our atoms, and like they're aligned on this sort of like black grid, and like the black grid isn't real, like materials aren't tied together with little strings. This is just like guiding your eye for how to look at them, and maybe like if you tugged on it in this direction, it's the same strength as if you tugged it on this direction, but if I just redraw those lines, and get like a pattern like this, these lines, let me just flip back and forth a couple times, like it's just supposed to be a visual demonstration. These lines are kind of closer together than these lines, and so you can imagine that if you kind of took this material and loaded it like in this direction, you might get a different mechanical response than if you loaded it in like a vertical direction. And so it's these sorts of different it's these sorts of different like elastic constants that are going to parameterize our problem. And it's all because of this single crystal property. There's also a little bit of an issue. There's also there's a little bit of a, what's the way to say it? There's an issue with it's important how this crystal lattice is aligned with the actual part. So you can imagine that if you were building like a bar of material, you might want to imagine the bar is going to be like loaded longitudinally or something. It's going to be loaded in like the long direction of the bar. You might want to like line that up with a certain direction in the crystal lattice, and that's true for the materials we work on as well. If we're going to estimate the resonance constants attached really to this intrinsic crystal lattice and not the sample itself, we have to estimate this weird sort of misorientation parameter. I haven't explained that very well, but just know there's like sort of a hidden misorientation we have to estimate in here. This is vaguely, this is actually going back to the one parameter model. I kind of switch back and forth between complicated and simple, but this is the model that is kind of fit in the attached Markdown notebook. Like I said, our statistics are really sort of primitive. It's just sort of a measurement error model. So we have our model, we have our like eigenvalue problem that I talked about, and we're just saying our data is normally distributed about it. There's nothing really exotic about that. The trick is just how do we do these eigenvalues fancy, and how do we use custom autodiff to make these eigenvalue solvers fast? That's what the Markdown notebook goes through. I won't dwell on it here, other than to say that if we actually generate data from this model and then fit it, the red lines, I don't know if you can see them very well there. It's a two-parameter model. The red lines are the truth. The rest looks like we fit our parameters. The other thing is just a histogram or whatever of our posterior. All right. So this is kind of an exciting slide for me. So like, if we accept on our last slide that our basic little model is working, and then we go code up our complicated model, then these are the results that we might get. And these are each line here corresponds to a different STAN calculation or whatever. It's a different set. So in this case, we took a sample of some sort of cobalt nickel superalloy, put it in the little test rig, measured its resonance mode, and then ran a STAN calculation on it. In each case, we did like a replication of the experiment. And so here you can see a bunch of mechanical constants and our uncertainties of them and stuff. And so this was kind of cool. I think my collaborators like kind of finished running the calculations for this probably a couple months ago or something, and I was really excited to see this. And this brings us to the point where it's like, okay, is our job done? And our job is never done. So let me go ahead and tell you about sort of the weaknesses of this analysis. Like, first of all, because of sort of like the computational difficulty of working with like an eigenvalue problem embedded in a statistical model, each row in this table, so each row in this table is like, it's one sample. And like, if I wasn't talking to you about mechanics, if I was talking to you about healthcare, or if I was talking to you about political science, you would already be laughing at me that I'm trying to like maybe come to conclusions from like one sample. So like these are not like estimates of the elastic constants of CMSX4 that you might actually deliver to an engineer and be like, use this. And so the question is like, well, how do we get it to that point? Well, we get it to that point by actually taking populations of samples of CMSX4 and doing our inversion on it, the same thing we do with everything else. But we're kind of limited computationally there. Okay, so that's a real problem with this analysis. Another thing, oh crap, I know there's another sort of obvious flaw here, and another thing is, once we went through all the hard work of running these calculations, and each of these sort of simulations, they might take a day to run. After we got through like all the hard work of running these things, like it was one of my collaborators like just decided to run the Stan optimizer on the problem, and it worked. And we originally started doing sampling to solve our problem because our optimizers weren't working, and so it was a bit of a weird thing. Is it's like, oh wait, so like we spent all those months and months and months stressing ourselves out about Bayesian inference and sampling, and we could have just been optimizing. And so it was a little bit of a weird feeling. And so we have like there aren't many parameters in this problem. I think like I'm showing you for each of these things. There's 3 here. There's about 4 that are hidden. But this is definitely the type of problem that like appeals to like a Laplace approximation. Like we could run an optimizer, do like a sort of like multivariate normal approximation of the posterior, and probably do really well. And so why did we do Bayesian inference, and what can Bayesian inference do for mechanical engineers and everyone like us? I think the answer to that comes in the model development. And so I'm nearly done. And this is kind of the conclusion of this presentation, and this is what I'll tell my bosses going forward, because the honest truth is we can solve a lot of these things with optimizations. Now that we understand the mechanics and the models correctly, and now that we understand some of the samples that we're testing more. But during the process of figuring this out, this is one sample that we were working with, and these are like pair plots of 3 misorientation parameters, and the misorientation parameters. This is the sort of the rotation of the crystal lattice with respect to the part. Each of these parameters can vary from between -1, basically -1 and 1, and you can see that in this calculation, every single parameter is varying between -1 and 1, and it's not in some sort of like trivial fashion. It's not that like the misorientation doesn't matter. It's that this non-identifiability in our model exists on some sort of ridge. And so what this is telling us is that there's something really interesting about the sample that we're working with that we didn't think about before. And I think the running hypothesis on this is instead of a single crystal material, we're actually in fact like working with a material that has kind of like think of it like columns of material kind of glued together and then cut out into a square. But the hypothesis, and we haven't really like verified this yet, is that this material has an extra bit of symmetry in it, and this sort of insight into the problem is like not available with optimization and stuff. And so this is really what Stan did for us, and this is really what sampling did for us. And so that's it for my presentation. If these are my wonderful collaborators, if anybody has any questions, go ahead. Boink, boink, boink,
Do we
boink.
have questions?
I've got a comic strip.
Oh, sorry.
Thanks. The first question I have is, have you done comparison with some standard tests, such as Coulomb tests with your C11 and C44?
Oh, so like just simple, this sort of like the...
Right, those are standard testing in the industry.
Yeah, so like, the answer is yes. It's limited, like we've done like limited tests with these, so like sort of conventional. And I'm not the material scientist here, but you're talking about just like load a dog bone at 2 ends and like pull it.
Right.
Yeah. Okay. So we did that for like a CMSX4 sample, and like everything lined up pretty well. Like that comparison is in. I mean, there's a paper back here. The answer is yes. The real answer is not to my satisfaction, and I would like to do a lot more. Kind of the issue is that table of materials I showed you, they're all kind of weird exotic materials that were just laying around a research lab. We really should like go get some single crystal samples of like copper and aluminum and like actually do this sort of test, but kind of the material scientist I'm collaborating with on this is graduating, and so hopefully we can do this sort of thing in the future. The other thing is like the misorientations, and like, oh my God, like we've only really confirmed like our estimates of the misorientations. Like we only really have like one sample that we've done that on, and like it's not an exact fit. There's some sort of clear problem. But like at this point, I trust the calculations more than I trust that X-ray measurement. So there's like a lot of work we got to do there as well, just like sort of brute force getting samples and verifying.
Yeah, that's kind of my next question, which is I mean, for the concern of aerospace industry, apparently next step would be identify the property of fatigue and creeping. What do you think the framework of the Bayesian analysis could be improved toward those tests?
Yeah, this is a really interesting question, and like I think it's I've been hanging around because this is just work with one of my materials buddies. Like I've been hanging around other people that do the creep tests and stuff, and like I think this question gets extra interesting in the context of like the additive manufacturing stuff, where there actually is like significant variability in like the production run-to-run productions of these things. My answer is I don't really know, but like, yeah, like if you want to talk about it, like, please, like, I'd love to. It's really interesting to me.
Very quick question. I got one.
Oh, yeah, go ahead.
Can you give me a crystalline analysis of this?
Let me check the name on this. Oh, this isn't the SS Petzl, so, but it's all right. It's all right. Actually, yeah, before I go ahead and get down, Aaron Goodman, the guy with the cap, we are going to be doing, I hopefully with Breck's approval, we'll be doing like a time series, like non-parametrics, birds of a feather thing later today. So if you want to talk to me and Aaron, like please come by that if you're interested in time series and Gaussian processes and stuff.
All right. Cool.
Yep. Thank you, everybody.
Thank you.